Okay, so our second presentation today is from Bhargavi, if you'd like to come up. Bhargavi is an experienced researcher and academic with a demonstrated history of working in higher education. She is skilled in data communication networks, network security, and designing networks for varied industrial requirements. Besides being an ethical technologist and a renowned contributor to education, research, and development, she's currently pursuing her research on smart grid communication networks at QUT. So Bhargavi's presentation today is titled Designing and Optimizing Neighborhood Area Networks of Smart Grid. Thanks, Bhargavi.
Thank you, Jack. Okay, I'll share.
Yeah.
But all right. So you already know what is the title of my topic. So I'll directly go to the problem statement. Now, smart grid is, we have already existing the power grid, the power systems or the power network, and we want to build an IT network or a communication network on top of it to make the power network intelligent. That is what is all about smart grid. So smart grid is the target in Industry 4.0. In 2021, it was 43 billion, and it is expected to be crossing the 100 billion by 2026. Australia will follow the trend, and NAN is what is our focus. So smart grid actually is the generation, and then transmits, and these are the consumers. So we want to provide a communication network which will serve this network. So neighborhood area networks, if I define it, it is a last mile technology which is connecting the substations control center to the smart meters. That's why its scale is very large. Because the scale is very large, and it is now, we don't want any more wires because we already have a lot of connections to home, we prefer wireless. So wireless network is desirable one, but it is challenging because of the two factors. First one is the scale, and second one is the latency. This is what is existing. We have a control center statewide, and they are connected to the generation, the transmission, and the distribution, which ends up in the smart meters, which are serving all these customers. Now this is already existing, and we want to develop. Partially this is already existing with the support of fiber, but neighborhood area networks is what is the challenge. So control center to substation, and through wireless network we want to connect the smart grids. This is our focus. If we isolate our problem from control center to smart grid, we would like to provide a communication network. Now these are the research questions. We would like to design a communication strategy that will fulfill, first one, the low latency requirement, and second, we want to scale the delay proficient communication strategy to the thousands of nodes. These are some of the objectives. We would like to solve the problem mathematically and simulation based to achieve the transmission mechanism that is low latency and large scale. Now we design this architecture. For that, first we have done, there is a power system, they have a smart grid architecture, and we IT people believe in the standard model of OSI and TCP/IP. So first thing we had to do is to align these two or map these two. So we can see that power systems and control system devices. So power systems have these three architecture distributed, and then these physical devices are served by these devices, which is power control. Now these power control and power systems align to our physical layer, and then the communication layer, there are three layers, data link, network, and transport, which is aligned to these. Now these are the ones which is existing, and we are supposed to provide these two. Also there are some of the proficient, available, or compatible technologies which can serve. Then comes the security and application layer, which is aligned to these three layers, and then that has somewhat some development and much maturity is needed. We identified the wireless network and wired network, both of them, the technologies which can serve the purpose. The two major factors which we wanted to identify is what data rate it is providing and what is the coverage area. Because it is a last mile technology, the substation area is around 5 kilometers wide. So to provide a network which is 5 kilometers wide, where one substation exists and control center sits there, then we need also the area to be considered, that what is the range of that technology. Finally, with rigorous efforts and literature review, we identified 26 applications that have, so there is a 2 sections of this table. Now these are the applications which we need to serve. Now we have defined, or we have divided these applications into 2 categories. Some of them needs real-time or very quick or no delay transmission, because the delays may lead to the data loss or some blast or some huge capital loss. So to avoid that, we need a very quick communication mechanism that are highlighted in red. All others can tolerate the delay up to 5 seconds. But these ones, it's like very quick. So that's why we have the communication which can be around 2 seconds, but not more than that. So therefore, we have categorized them into these WAN, HAN, and NAN, the coverage area, the bandwidth, the latency, the power backup, and then we define which technologies can serve these applications. So that is the standard, the technology, and the protocols, or the sticks, that is RFCs. So there are some 26 identified these applications, and we would like to solve these or serve these applications. So first of all, there are 3, now if we identify, there are 3 major needs. How can we serve the real-time applications? How can we serve the non-real-time applications? And how can we serve the scalability? So we divide it into 3 sections. First of all, we'll have a look at how we solve or serve the non-real-time applications. For doing this is our problem statement. We wanted something with as a hybrid technology combination to design and solve the problem, which is serving densely populated and sparsely populated areas. The application requirement may not be time critical, but 5 seconds delay is what is the maximum range we have set. We also would like to design it, but that is challenging because the smart grid needs to meet the application requirements of scalability also. So we designed this as a solution. Now this is a home area network where wireless node or router connects all the equipments and then connects to the home. And then these homes, we need to connect it to the control center. Therefore, we design a 5G base station using cell MIMO MMTC, and then we connect it with a fiber to the 5G core, which reaches to the control center. Now we can see the red lines are all existing power network which passes the electricity, but the wireless network which we have designed should be served with the help of 5G small cell, fiber, and 802.11 and some sensors. This is a mathematical model considering the time constraint. I'll not get into it, but we have divided the 5G slice into the number of users, and this is the number of users can serve the equal or fair share of resources if we have the number of users within the threshold limit. Similarly, we have followed the slice sharing, so proportionate fair share resources can be achieved. Now, practical scenario, if we talk about, we have defined it into 6 different scenarios, and this is the table indicating the 6 scenarios, and then the number of devices we have used and what it connects to and what it. So let me discuss it, the topology. This is a screenshot of the implementation. If you can see, this is a power generation and storage. The violet area is a control center. This is a backhaul network supporting all the servers, then connectivity, and the power batteries communication. Then we have a home router which is connected to the individual gateways, and then this is the neighborhood area network which has multiple power meters, consider it as a society, and that they are connected to the appliances of home. Now we can see that a successful communication is built with all the green dots indicating successful communication happening. Let us see what the performance analysis of the latency says. Now we have observed 3 major parameters which helps us understand how the latency can be understand or can be analyzed. So out of these 6 scenarios, that is home 1 to home 2, main server to backhaul, main server to home router, home gateway to home gateway, home meter to home gateway, and solar panels to main servers, we have identified that the maximum value here is 309 milliseconds, which is between home 1 and home 2 because of the congestion. Minimum 1 second is found between solar panel and main server, and 20 seconds after that the network becomes stable and it behaves in a range where 17 to 49 milliseconds we could complete most of the scenarios. The end-to-end delay, if we talk about, we can see that here within 40-45 seconds, most of the scenarios are there other than this one. So 96% of the packets traversed were less than 10 milliseconds here. So thereafter, we have seen the flow completion time. We can observe that within 14 milliseconds, most of the flows were completed. This is how we can say the contribution. We could solve the problem of majority of the white font applications, but still the red fonts, which were the real-time applications, has yet to be served. So for that, we can say there are still 2 more limitations we need to achieve, that is the real-time applications and the scalability. Therefore, now we focus on the real-time application serving, and we designed, so we bring in the real-time networks. Now, real-time networks are those networks which you use in the, for example, cars. You brake it, immediately it shows. Your tire air is not proper, immediately it shows. It doesn't wait for a second also. So that's what the real-time networks, it's used across the world, also in the smart grids, for example, elevators, and there are a lot. But considering the smart grid applications for monitoring and controlling power supply, for automated outage management and faster restoration, these are the 3 major applications we need real-time. But integrating high-level policy of delays is challenging. So we think that software-defined networks can serve the purpose, but then we need to do a proper handshaking between software-defined networks and real-time networks. For doing this, we have defined a mathematical model. I'll not go in depth into it. I'll move forward to the real architecture. So we can see that here there is application plan, and then this is what is the network. Now this is what is real-time switches and hubs, which is serving these applications. These are the smart grid components. And to serve them, we will bind it with the open flow protocol of software-defined networks, which will serve the purpose of imposing the policies through SDN controller, such as admission control and all. This is open flow protocol. The input port will be having the set of actions at ingress port, do the constant configurations, and then take the action based on this planner, whether the packet should be sent to the output port or drop packet or should be under the observation. And we have a proper handshaking done with the APIs between OpenFlow and real-time to achieve the target. These are the results. The left side is all about the RTN network and the right side is all about the SDRTN network. Now, first 2 parameters are talking about the bandwidth constraint, and the last 2 parameters are talking about the latency constraint. Now, if we talk about, there are 4 lines in there: the maximum value, the minimum value, the median, and the standard deviation. Because it is difficult to understand from the graph, we make it into the tabular form to understand and analyze the data very well. Now, this is very easy, where we have defined all the values and comparing RTN with SDN. First of all, the throughput, then packet loss, then latency, and then jitter. We can see the overall gain is really large overall in the throughput. Also, the packet loss, latency, and jitter are reduced drastically in SDRTN. So we talk about 217% of gain in throughput, 71.7% in packet loss, 69.7% in latency, and 73.6% in jitter. Therefore, we can say that SDRTN improves the performance, it is lightweight, and it serves the real-time applications. So overall contribution, we can say that we have achieved 2 of the using logical and physical networks communication strategy. The first one, all the 26 applications are served, because we could serve the remaining 7 real-time applications with this communication strategy. Still, the latency is a question. For latency, we come up with the third, that is node allocation strategy for scale-free networks. Now we need a wireless connectivity, but the challenge is large scale, how to serve it. What is the solution? We can have intermediate nodes which can be directly connected to the utility node or the control center to solve the problem. So therefore, we come up with a two-layered topology that will minimize the hop count or intermediate nodes and reach to the scale-free network. Consider this as a physical electric smart grid network and this as a communication. Now here we have all the smart meters. These are the upper layer which is helping the transport, and this is where the control center sits with the substation layer. Now to make it reach, they have just now done some, we can do in the similar fashion, which they have connected it with the copper or Ethernet or fiber. But we need a wireless solution, so we would like to identify the red nodes in the existing smart grid and then connect it directly to this control center. So this is our focus. Consider this is the real scenario. Now these are the smart meters in a society which is connecting to the substation, which is a green node. Now black nodes, there is an easy connectivity, there is no problem. But what about the blue nodes? How many intermediate nodes are required to connect these blue nodes? So that's the question. So this is a mathematical model where we are defining the X as all the nodes seeking connectivity to the control center. Then we identify the H, which is, if it is more than that, means all the blue nodes forms Y. And then we define few of them from Y node, and Y set we pull it in the Z to make it reach to the less than the required. So this is the solution. What we do is we divide every area into small squares, and from there we build a local spanning tree. The local spanning tree range would not exceed more than 5 nodes. And from this node, we would directly connect it to the utility node. Therefore, now if we want to connect any node across the entire NAN network, the maximum hop count will be 6. This is one of the examples. Therefore, 6 nodes connectivity is fixed. Now this is also scalable. The reason is if I need the extension of my area, I just need to add 1 square, develop a local spanning tree. So this is how we have solved the problem of connecting the nodes. These black nodes we are not much worried about. The reason is they have direct connectivity. The number of intermediate nodes are very less. And this is the algorithm of generating the local spanning tree and the contribution. We have fixed the 6 hop connectivity irrespective of the shape, size, or number of nodes in the NAN. That's why we claim it to be scale-free. It is suitable for time critical because the number of hops are reduced drastically. So we can serve till end geographical location, irrespective of the geographical location of NAN. And 2D it can expand, not 3D, but as of now we don't need it, so it's fine. But the major takeaway is if there is any addition of a smart meter or deletion of a smart meter from the network, we have to just regenerate the local spanning tree of that square, not the entire spanning tree. So that's what is happening in the base paper, and we have overcome that limitation of the base paper. So conclusion, we have solved this problem using architecture mapping of OSI TCP/IP with smart grid. We have defined NAN communication strategy for non-real-time applications. We have also served real-time, and then we have also come up with a scale-free. So all the 3 objectives are achieved through this. These are some of the publications. 2 are published and few of them are in draft and in review. Thank you and welcome to the questions. Yeah.
The node allocation strategy, what about in places where the with the node allocation strategy, what about in places where the population density is a lot lower?
Yeah,
like out in the outback.
It will serve the purpose. The reason is that even if the density is lower, the number of nodes in single square will be less. That's the only thing. But we can build the spanning tree connecting to the route selection. Also, one thing to mention that the route selection is using Prim's algorithm, so that we don't predefine who will be the route. The one which has the shortest distance with all the nodes is selected.
So it's automatically, so it's dynamically works out which one is the cluster center or whatever.
Yeah, so we first of all build the spanning tree, and then we decide who should be the route.
Yeah.
So.
Thanks for your talk. I actually have a flotilla of questions. I'm sorry. Yeah, okay. I'm just curious about how you came up with the latency, your target latency. The reason I ask is because, number one, it's too short for control. It's too long for control. But if you're wanting to do real-time modelling, as in a very, very short period of time, it's possibly too short. Again, with the real-time modelling, given the Australian circumstance where billing is done on a 15-minute interval, you probably want it maybe 3 times in that 15-minute interval, just picking a number out of my head. I'm just curious about where you came up with that latency.
Yeah, 5 seconds.
Yeah, 5 seconds.
Yeah, so if you see here, there are some applications which we have identified which needs real time. For example, demand response state-wise. For example, there is a blackout in one of the states. There is a chance that other states, it will start pulling the things. So that should not happen, that cascading blackout should not happen from New South Wales to Queensland to every other. So to avoid that, we need to, like, there is a blackout and the power pull is happening from New South Wales to other states, then there is a chance we can avoid it at immediate. There is no chance that a call can happen or a control administrator is allowed to do it. So that's one of the examples.
So what you're saying is, in that circumstance, that latency time has been
very crucial,
targeted at the state estimator, essentially.
Yes.
Okay.
So these are red phones I have listed are the ones which needs. So we cannot provide automation without real-time involvement. Automation.
No, of course,
yeah.
of course. The second thing is that the Australian network, electricity network, is quite a different architecture to that of Europe and the US and North America, South America. Is this very transferable, or is this something that is specific to the Australian situation, or is it more aimed at the North American market, for example?
Yes, so we scaled our research to the neighborhood area networks. We scope our research to neighborhood area networks. So neighborhood area networks is just dealing with control center of smart substation to the set of smart meters serving the nodes. So this is the only, so that is applicable to 5 kilometers range wherever the population is.
Right. Well, I mean, that's probably more a North American type of target, whereas with, I mean, for example, substations here in Brisbane, the feeders are 20 kilometres long.
Yes, but then there are substations who are serving CBD as well.
True,
yes.
True. Yeah, I mean, in the city, every building's got its own substation.
Yes. So that's why the number of nodes range from 50 or 20 to 5,000. That's
right.
Thank you very much. Any other questions, Will? Or those people online, if you have a question,
yeah,
don't see it in the chat though.
No. If somebody's talking, no, maybe me. Yeah.
Okay, great. Thank you, Bhargavi.
Yeah.
Thanks for the presentation.
Yeah.